let's talk about escape velocity. I want to do this in a little bit different way, but so let me first start off with the situation. Suppose that we have the Earth. I drew this, and we have some object that's launched with an initial velocity, and there's no air resistance, there's no rockets, it's just given some initial velocity. You know, it's going to move around, and it's probably going to come back down. And the faster you go, you throw that or shoot it, the further away it's going to get. Is there some value of speed such that it will go so far away that it never comes back? That's the escape velocity. And yes, there is. There's a speed that you can throw this and it will never come back. Okay, so what I want to do is to first model this situation with momentum principle. And then we'll calculate the escape velocity with energy. That's where we're going to go. But I want to make a model. I want to make a visual model of the motion just so we can have something to play with and make a graph of. So it's going to take a little bit longer, but I'm willing to spend the time because I want to do it. So if I have some object right here, a vector distance r from the center of the Earth. Now, I'm going to put my Earth at the origin just so that my vector is a little bit easier. The Earth's not going to move. If I know that vector value r, then I can calculate the gravitational force on the object up here. It's going to be negative g, that's the gravitational constant, mass of the Earth, mass of this object, divided by this distance squared. You got to take the magnitude of that vector to square it first. And then I need this r hat. So this negative and the r hat says that the vector direction of that force is this way. And that's kind of important, right? Because as this moves around, I don't want to just find the magnitude of the gravitational force. I need to find the vector value of the gravitational force. And so if you don't have that r hat, you don't have it. With that, I can use the momentum principle. The momentum is mass times velocity. In this case, we're not moving that fast that we can't use that. So mass times velocity. And the momentum principle says that the total force on an object is the rate of change of momentum. And I've written this as a finite difference, delta p over delta t. Let's say we take a small delta t, and I'm just picking a value, I think this will work. Delta t equals 10 seconds. So in 10 seconds, if this is moving really fast, it's going to move and be in a new location, but it's not going to move that much. It's not going to move that much, such that we could approximate this gravitational force as being constant. So the net force, is the only force acting on it, would be constant. If that's the case, then I could say, I'm going to call F net Fg. I can write that as P2 minus P1 over delta t. So this is momentum at the end of the time interval. This is the momentum at the beginning of the time interval. And that's my time interval. And that's a g. I'm just very sloppy. So if I solve this for P2, and I've done this before, so I'm not going to spend a lot of time on this, I get this. So I can take that time interval and find the momentum at the end of the time interval. Next, I can say the average velocity VAVG is the change in position of the mass with respect to time. And if I can approximate that as P2 over m. So the momentum I just updated, I'm going to pretend like that's a constant velocity even though it's not. And so I can use that to solve for R2 and get a similar equation. R2 is R1 plus P2 over m delta t. So we just made a numerical model, right? Because if I want to do the next 10 seconds of motion, I can do the same thing. I just go back up here. I have a new r, so I'm going to have a new gravitational force. So I'm going to first do this. And then I'm going to update the momentum. And then I'm going to update time. And then I'm going to go back up here and do it again. I just keep on doing that over and over and over again. And so we're going to do that in Python. I partially built this model because I don't want to spend too much time on this. But I want to launch this with a time step of 10 seconds at, let's say, I think I picked 3,500 meters per second. So V0 is 3,500 meters per second. And let's see what it does. And then we can try changing the speed and doing some other stuff. So switching over to Python, and we're going to I really want to make a graph. That's what I'm going to do. So I've already got a bunch of stuff in here. Let me tell you what I have. Gravitational constant, mass of the Earth, radius of the Earth, mass. That's the mass of my object. It doesn't really matter what that is. And then I have my Earth. It's a sphere. The mass is also a sphere on the edge of the Earth on the x-axis. And there's my initial velocity, my initial momentum. And I wrote that in a weird way. I wrote mass times velocity. I want to give it an initial speed. And then this vector 1, 0, 0 says I'm throwing it in the x direction. And I took the unit vector of that, even though it is a unit vector, so I can change it without having to worry about changing the overall speed. Let's just run this. So there's my Earth, and there's my object right there. It's on the x. I can't really see it too well because of the where it's at. Okay, so now let's just do something simple. Let's say while t is less than, I'm just going to pick a number here. Let's say 1,000, and let's just see what happens. And I will say rate 100. So rate tells it how many steps how many loops to do per second. So this will run at 100 calculations per second. You can change that to change the animation rate. And the first thing I'm going to do it this way. R equals mass.pos. So mass.pos is the vector location of the object. But I'm going to call it R just because it looks better in the equation, and I like that. So now I'm going to calculate the gravitational force, negative g times mass of the Earth times m times norm r. Norm r is a unit vector. That's r hat. Divided by mag r, that's the magnitude of a vector, and then squared. Star 2 is squared. Now I'm going to update the momentum of that. I already gave it an initial momentum. So mass.p equals mass.p. Is this big enough? That's big. Mass.p plus f times dt. Now I'm going to update the position. Mass.pos equals mass.pos plus mass.p times dt divided by m. And then finally, I just need to update the time. T equals t plus dt. Let's run it. And there it goes up and then back down. And it actually went into the Earth, and that's fine. Let's change this up. Instead of doing it for, I don't know how long it's going to take to go up and back down. And that one did not escape. I don't know if you noticed that. So let's do this. While mag of mass.pos is greater than or equal to the radius of the Earth. So it's going to go up and back down. As long as it's greater than the radius of the Earth, it's going to keep running it. So we should get about the same thing. There it goes. Okay. Now I want to make a graph. Let's make a graph of, and this may not make sense right now, but I'm going to make a graph of the velocity of the object as a function of position from the center of the Earth. That way we can see how it's moving in a way. So I'm going to make a graph. G1 equals graph. Let's just give it an X title of R. And I'm not even going to put the units there. I'm just trying to get this quick. Title equals V, and I do want to put the width equals, let's do 500. Height equals 600. Just to, 250. And then F1 equals G curve. Color equals color dot blue. Dot equals true. So dot equals true is going to be useful for here in this case because we're not plotting it versus time, but the dot will show us where in time we are. So now down here to add a plot to that and say F1 dot plot, I want to plot the R value, which is just going to be mag of mass.pos. I could actually use R. And then the velocity is mag of mass.p is momentum, but then I need to divide that by m. And I think that will work. Let's see. Okay, there it goes. So it went up here. It went up. I want to run that again. I want to see it this time. There it goes. Okay. So it went up and came back down. Yay. Now, I want to make a second plot. I want to redo this. I want to make two graphs. I want to show you what happens. What's going to happen if I don't launch it straight away from the Earth, but at an angle? This is kind of a cool thing. So let's do this. Let's make another curve. F2 equals G curve. Color equals color dot red. Dot equals true. And then down here, I'm going to copy all of the. I'm just going to. This is not the best way to do it, but who cares? I'm going to copy all this and repaste it. And I do need to re-put the mass. I need to put the mass. I'm resetting everything. Mass.pos equals vector RE00. That's what it was, right? Vector, yeah. So I reset the time, reset the momentum, but now I'm going to give it a momentum 1, 1. So it's kind of like in the positive x and y direction. Still going to have the same speed. But let's see what this curve does. Oh, and I'm going to change this f to f2. So I'm going to plot it in the red version. Okay, let's do it. So it's first going to do this one. So it goes up and then back down, and then it's going to do the other one. Okay, now let's watch it. I'm going to rerun it, and let's watch the curve. So there's the up and back down, and this is the other one. Notice the same curve. It doesn't go as high, it doesn't get as far away, but it's on the same velocity versus position graph. And you'll notice that up here, this one gets to a velocity of 0. It went straight away, it stopped and came back. And this one didn't, okay? But it went a distance of 7 times 10 to the 6 meters away. Now what if I increase the speed, let's say to 5,500? Run that. Let's watch it. And then, so there's my first launch. And the second one. Okay. And then if I look at the two graphs, you'll notice that they agree. I'm not going to animate them. But it's 8.3, so it did go further away. Let's do one more speed. And let's do 8,500. That one goes up. So I'm trying to show you it doesn't matter about the total distance. The maximum is going to be when you get shoot further away, but it'll still go away with the same velocity versus position curve. There's that one. It's going to still hit. And so you'll see here it's coming up there. This one's going to end up going. I won't let me look for it yet. Okay, so 1.5 times 10 to the 7th. So it went further away. So you can see eventually we're going to get to the point where maybe it's not going to come back. It keeps going further and further and further. Okay, let's calculate how far that goes. Now I'm going back to the paper. Because one thing we don't care about, and I showed this in the plot, we don't care about the time. I don't care about the time. If I don't care about the time, then I should use the work energy principle. So this says the work is equal to the change in energy. In order to do this, I need to define my system. So let's say the system consisting of, I'm going to call it a ball, whatever that is, plus the Earth. And so once you define the system, that has an impact on both of these. So this says that if I have my Earth and my ball as my system, then the work is going to be due to anything interacting with the system, and there is no thing interacting with the system, so the work is 0. But it also says that the change in energy, I know what kinds I have. I can have a change in kinetic energy of the ball plus a change in kinetic energy of the Earth, because it's part of the system. But I also have an interaction between these two. So I have to have a potential energy. So it's going to be a change in gravitational potential energy. I'll just call that delta U. And so the Earth doesn't move, we're going to assume. And we define kinetic energy as 1/2 mv squared. And I can calculate the gravitational potential. I have a video on that. It's negative g, mass of the Earth, mass of the object, over r, the distance from there. Okay, so let's take a ball and launch it with some initial velocity v0, and let's say it comes up here and it's gonna come back down. Let's see how high it goes, and we can use our calculations to see if we agree with the simulation. In this case, I'm shooting it directly away, so I do know up here let's call this v1, v2. v2 is equal to 0. So let's put everything in our work energy equation. I know the work is 0, and that's going to be equal to delta K ball plus delta U. And I'll leave off the Earth. So it's going to be K2 minus K1 plus U2 minus U1. That's change in. And I know that up here at point 2, the kinetic energy is 0, so that's 0. But these are not 0. So let's start this at the radius of the Earth, and let's find R2. So I can write this as 0 equals negative 1/2 m v1 squared plus U2, which is the potential energy up here, minus g mass of the Earth, mass over R2, minus the initial potential, which is also negative, so it's actually going to be plus G, mass of the Earth, mass over the radius of the Earth. And I want to solve for R2. So let's add this term to both sides, and I get G, mass of the Earth, mass over R2 equals, and I'm going to change the order of these, G, mass of the Earth, mass over the radius of the Earth minus 1/2 mv1 squared. Now, the first thing you should see is that these masses cancel. Those masses cancel. Now, I want to solve for R2. It's not completely trivial, but it's not impossible either. I'm just going to write this in a messy way, and then we can calculate this with Python, because I want to enter all those numbers. So really, if I divide both sides by this, I get 1 over R2 equals, I'm dividing by GM, so I get 1 over the radius of the Earth minus V1 squared over GME. And now I can just flip both sides. I'm not even going to get I guess I should get a common denominator. I don't want to be a barbaric. Let's just do that anyway. Okay, so I'm going to write this equation, 1 over R2, 1 over RE minus V1 squared over GME. I wasn't going to do it, but now I'm going to do it because I felt bad. So if I get a common denominator here, I get 1 over R2 is going to be equal to, I don't know why I did that, GME over REV. I have to multiply this by over RE times GME. That's excessive 1. I just blanked out there for a second. Minus V1 squared times RE. Yeah, that's right. And then I can flip that. So now I get R2 is the radius of the Earth times G times ME over GME minus V1 squared RE. That looks messy, but it's not that bad. Let's put in our values. I'm actually going to calculate this in Python. So let's say that V1 equals, what was my last value that I used? Because, Python is the best calculator, 8,500 meters per second. Okay, so let's just calculate that. I'm going to switch over here to Python and print that out. So let's go down. Oh, I need to switch. Sorry. So here we are. Down here at the bottom, I'm going to add in, I'll call it RT for theoretical. I'm just going to type in that equation that I see right there. G times mass of the Earth minus, here I called it V0 squared times the radius of the Earth. I'll put it over here, RE times all of that divided by RE times G times ME. And let's print that. Print R max theory equals RT in meters. So let's run it. And let's just hope that it works. Okay, so it's going to first do this shoot up, come back down. It's going to go up. It's kind of curious that that's not a straight line. I'm kind of interested in the shape of that line now. It's not straight because we're plotting position versus velocity versus position, not time. And then the second one doesn't go as high, but it goes pretty close. I probably should just cut that out. And coming back down. And then it will calculate R. Oh, that's wrong. I made a mistake. That's not even anywhere close. Okay, let's do this. Let's change this. I assume I made a problem with my common denominator, but I can fix that in Python. So let's just say 1 over, I'm just going to type the other equation, 1 divided by RE minus v0 squared divided by g times me. I didn't simplify it. And let's comment out this one because I don't need that. So I'll just do 1. And if I made a mistake again, I'm going to be in trouble. And just so you note here, it's going to go, what's that? I can't see that yet. I'm kind of scared, to tell you the truth. Because you can make mistakes, especially when you're making a video. You start thinking about Python, you start thinking about other things. So this is 1.49 times 10 to the 7th. And I get 4 times 10 to the 7th. Oh, now I'm in trouble, huh? Let's switch over to the paper and let's see if we can figure out what we did wrong. It's obviously a silly error. Okay, this is good. G, M-E, M over R. And so that cancels. Oh, I didn't have the 1. I'm missing the 1/2. The 1/2. The 1/2. That's it? Is that the only thing? Is the 1/2? Wow. And someone's probably going to, at the beginning of the video, saying, oh, you missed a 1/2. So if I go up here, and this should be a 2 down here. That can't be it. And let's increase this rate to 500 just because I don't like to watch it too long. It worked. Okay. Well, that's really good, though. That's really good. So now we can calculate the maximum height using energy. We don't have to do the whole numerical calculation. And now we can calculate the escape velocity. So the escape velocity is, I want the maximum height of infinity. Okay, so let's go back to the paper and calculate that. So let's just do this. So it's going to start right here at position 1, and it's going to go an infinite distance away to position 2. And up here, it's going to go to an infinite distance with a velocity of 0. So v2 equals 0. So it's perfect escape velocity. I can write the work is the change in kinetic plus the change in potential. That's going to be K2 minus K1 plus U2 minus U1. So K2 is 0 minus 1/2 m v1 squared. That's what we want to solve for now. We want to find out how fast it's going. Plus U2, which is going to be the potential energy at point 2 is 0, right? Because as U equals negative G M-E M over R, as R goes to infinity, U goes to 0. So this is going to be equal to 0 minus a negative. So I get plus G M-E M over the radius of the Earth. And I want to solve for that. So let's add this to the other side. 1/2 m v1 squared is G, mass of the Earth, mass over the radius of the Earth. These masses cancel. Multiply by 2. V escape is going to be G, the square root of G, mass of the Earth, 2 over the radius of the Earth. Square root. Okay, so let's calculate that in Python, and then we'll put our value at that and see what happens. And bad things are going to happen, I'll tell you right now. Bad things will happen because of the way I put my limit, which is fine. We can do bad things. Okay, let's calculate that. Let's calculate and run it. V escape equals square root 2 times G times mass of the Earth divided by the radius of the Earth. I mean, I should also check the units on that, but G is kind of a weird unit. Let's just go with it. And let's print that. Escape velocity is V escape in meters per second. Run it. And I got an error. You know why? Because I misspelled something. Oh, I see what I did. I put parentheses. See what? I put the comma. Oh, no, that's right. Escape. Oh, v escape. What was the error? I'm having a lot of troubles today. Oh, I didn't put a comma right there. Okay, that must have been it. Okay, there it goes. So the escape velocity is 11,176 meters per second. Let's just go ahead and put it to a little bit less than that. Let's put it at 11,000, just for fun. Let's put it at 10,000. 10,000 meters per second. So my V0, let's put it at 10,000. 10,000. And let's run it. And it's going really far away. Oh, it's come back already. So it didn't go that much further. But you'll notice that when the velocity really starts to decrease as it gets faster and faster. Let's just do 11. So I just increased by 1,000 meters per second. And you'll notice that at some point, it starts to barely change its speed down here at the end. It's not really changing like it did before. So it really has a chance to get very, very, very far away. And it will come back. So it's not quite the escape velocity. If you get it over the escape velocity, this will keep running forever because it's never going to get back down to less than RE, the radius of the Earth. If you plot, this is velocity, but if you plot v squared, it'll be proportional to the energy. You can do a whole bunch of other plots too. But the key thing is I have to have enough initial kinetic energy to get far enough away so I have zero potential energy. I can make another plot for this, but I'm going to do it later. I'm pretty happy with that. But look at what that escape velocity depends on. It depends on the mass of the planet and the radius of the planet. That's it. If you're starting from it really depends on the starting position. And if you start on the surface of the Earth, that's the radius of the planet. Okay. There's some more escape velocity stuff to do, but it's a good example to show you when it's better to use work energy than momentum. And I'll give you a link to this code down below.